recorded. Hopefully it works. My screen recorder has been a little clunky lately, but we'll see. All right, so that brings us to today. So here we are, right after the midterm. Good job getting through all of that one. And then I was looking ahead, and then just sometime shortly after Christmas, we'll have our second and final test, which will be final. The second test, I guess, final. It's non-cumulative, but first subject that's going to be on the test will be the information that I am starting on today, which is gases. So I'll do an introduction to the various gas laws today, work some problems on the first one, which is Charles's gas law, and then we'll get, we'll finish that off, and I'll give you all the homework that you need to do that in our in-person class next week. Okay. All right, so there we are. Okay, so gases. Let's look at that. So the first things that we are going to be looking at briefly, the theory of gases, which is useful. I mean, it's not entirely accurate if you're finding like most of these things aren't physically what actually happens, but they're useful approximations for get us through most everything. And we'll look at, there's going to be four things that we'll be looking at in order. We're going to start with Boyle's law. We'll go to Charles' law, Gay-Lussac's law, and then put all of those together, 2, 3, and 4, into the combined gas law. And we're just basically adding and dropping out different variables as we move through Boyle's, Charles, and Gay-Lussac's law. This will all make sense as we move forward and we fit it all together. And then we'll end somewhat briefly with the Avogadro. We're going to be talking about large numbers of molecules, and we're looking at Avogadro's, and Dalton's law, which is actually probably the most straightforward of the whole thing. All right, so let's see. So we'll have Charles's law. Nope. I'm going to have Boyle's law to start with. Do these in order. What? Boyle's law, Charles's law, and Gay-Lussac's law, and then the combined gas law. Okay, I'm going to circle back to that later and just look at those. But that's the way I recommend you keep track of these as I go through them, and you'll see they'll fit together like a, I don't know, Rubik's Cube. How about? Sorry, background noise. All right, so properties of gases. First of all, oxygen is currently at 21% of the air we're breathing. Nitrogen is far and away the most plentiful gas in our atmosphere at 78%. And that gets us up to 99% of our atmospheric gas on planet Earth. And the rest of it, like you'll know, things that we hear about, ozone, oxygen with 3 instead of O2, and carbon dioxide is just a fraction of a percent of our atmosphere. So that greenhouse gas, carbon dioxide, doesn't take much of it at all to really affect our temperature on this planet. And throughout our history, the planet's history, these have changed. In fact, we used to have a lot more oxygen in our atmosphere. I think well into the low 30s, maybe 33% oxygen. And at that point, I find this fascinating. Insects, since they don't have lungs and they have to basically take in oxygen and breathe it directly from the atmosphere down to the cellular level, they will be able to get much larger. And we have fossils of dragonflies that are like 3 feet across, because, and bugs were freaking huge, is a take-home message there. All right, so 21% is where we're at now, and then carbon dioxide is that bugaboo that we all hear about, as regards climate change and global warming. All right, so all of what we're going to talk about essentially depends on our idea of thinking about a gas as a state of matter, where we have small particles, gas molecules, and atoms moving in straight lines until they hit something, the side of the container, essentially. Okay? They have essentially no attractive or repulsive forces. And essentially, you can put this in quotes. So that's where we get where things aren't exactly the way we're going to be studying. But we're going to treat them as if they don't have any attractive or repulsive forces. They are relatively far apart. They aren't packed in their gaseous state, and they have kinetic energy, and this the increase in temperature is the way we measure an increase in kinetic energy. Okay, a hotter gas means it's got more kinetic energy. Okay, and they're going to bang into each other harder, increase pressure. That's what this all counts on. Okay. So we have 4 variables that we're going to be looking at, and we're going to manipulate these variables as we work our way through these formulas. The pressure, that's the gas, pressure against the walls of whatever container it is. Basically a measure of how hard they're running into the side of the walls before they're bouncing back. Volume is, it should be up there. Oh, that's unfortunate. Now, makes it a little hard for me to relate. Okay, so the first thing, and I'll send you a copy of this. Believe it or not, we're talking about Boyle's law, Charles's law, Gay-Lussac's law, and the combined gas law. Okay, that's there. And so really quickly, that's what we're going to be looking at: Boyle's, Charles, Gay-Lussac's combined gas law, and we'll polish off with Avogadro's and Dalton's, which are relatively straightforward. The key thing is going to be numbers 2, 3, 4, and 5. Okay, that 21%, that was just my little informational, thing to get you fascinated about gases, if there is such a thing. And now that brings us right up to the variables we'll be looking at: the pressure exerted by the atoms running into the sides of the container, the volume, basically the size of the container, the temperature, which is a measure of the kinetic energy, which is measured in Fahrenheit, Celsius, Kelvin, all those other things. But you're going to have to dredge up. You're not done with Kelvin. You're going to have to especially know the relationship between Celsius and Kelvin to successfully do your homework sets, essentially. Okay, and the amount, we'll circle back to that when we look at Avogadro's, because we're going to be using Avogadro's number to measure the number of molecules in a given container of gas. Okay. And the pressure is measured in a bunch of different ways: atmospheres, millimeters of mercury, torr, okay, and pascals. We'll look at atmospheres, millimeters of mercury, and torr primarily, and volume, liters and milliliters. Okay. So the volume, that's a set number that will stay constant unless it is a variable. Okay, size of the container. Temperature, measure of the energy of the collisions of the atoms within. gas atoms and or molecules. Okay. And most importantly for today, we'll look at pressure. We'll measure first of all, usually in millimeters of mercury or torr. Atmospheres. I'll get into what these are here. I'm not going to worry about pascals and kilopascals. If you were doing maybe some physics with me, I'd get into pascals, but I won't. And what we see in this country, pounds per square inch, when you're putting air in your tires, that's just a measure of this exact property we're talking about. Okay, particle collisions. Okay, so tire about 34 pounds per square inch, 34 to 40 pounds per square inch in your cars. And so this is a rudimentary instrument for measuring the pressure of our atmosphere. You have a little pan of mercury and a closed tube where it has all the atmosphere taken out. And so the amount that the mercury rises in that tube is due exclusively to the pressure that the atmosphere above it is pressing down on the mercury. Okay, so it just so happens there's a fella named Evangelista Torricelli. Oh, must be Latin or Italian. Torricelli. So Torricelli, Torr, is where this comes out. And they found that at sea level, an atmosphere presses down with exactly 760 millimeters of mercury. Okay, 3/4 of a meter, which we set as equal to 1 atmosphere of pressure or 760 torr. So you can see each millimeter of mercury is equivalent to 1 torr. Okay, so millimeters of mercury and torr are they're interchangeable. And 1 atmosphere is 760 either of millimeters of mercury or torr. Okay. There we go. So as you go up from sea level, so right where we're right at 760 millimeters of mercury. If you go up in the Cascades or whatever, you have less atmosphere above you pressing down on you. So atmospheric pressure decreases as you get further away from the surface of the Earth. Okay. Just like if you're at the bottom of the pool, there's more pressure on you than if you go up to the top of the pool. Exact same properties, just gas pushing down on you instead of liquid. Okay, so pressure. So an atmosphere, we'll put these all equivalent. 1 atmosphere is equal to 760 millimeters of mercury, 760 torr. Inches of mercury, which we will look at, is approximately 30 inches of mercury. So when you're watching the news and they talk about barometric pressure, or they always talk about inches of mercury. So barometric pressures might be about 30 and a half right now outside. Pounds per square inch, that's what you see when you're putting air in your vehicle or your bicycle. And then Pascal and kilopascal we would look at if we were doing a more advanced math class. So here we are, various atmospheric pressures. The Dead Sea is actually below sea level, so it has higher than an atmosphere, 800 millimeters. Sea level is 760. Los Angeles, right at sea level. Las Vegas, then all the way up to the top of Mount Everest, okay, the highest mountain on Earth. Your atmospheric pressure has dropped all the way to 253. So about a third of what it is at sea level. And a third of the oxygen, if you do you follow me along here. So that's why people generally need supplemental oxygen to get to the top of Mount Everest. Okay, not enough oxygen to oxygenate our hemoglobin and keep us going forward. Okay, so calculations. So what is 475 millimeters of mercury expressed in atmospheres? Okay, let's look at that. Was that 475? 470, what is that, 475? Already 475. Oops. Millimeters of mercury expressed in atmospheres. Okay. And like we just saw, if you go back to that chart, you can double check me. There are 760 millimeters of mercury in one atmosphere. Okay. So we're back to dimensional analysis. Again, you'll see it over and over and over again. Okay. Make sure that these cross out. Divide 475 by one atmosphere and get your answer in atmospheres. Okay. And pressure in a tire is 2 atmosphere. What's the pressure in millimeters of mercury? So dimensional analysis once again. Let's follow along. A little easy math to kind of get your brains going today. Okay, and like we just saw, for each 1 atmosphere, we have 760 millimeters of mercury. All right, let's make sure that we did this correctly. And atmospheres cross out, leaving with our millimeters of mercury, and that will give us our answer in millimeters of mercury. Okay. Uh-huh. 0.625 and 1,520 in both cases there. All right. So kind of the last thing I'm going to introduce to you, and then we're going to go through similar things through all the laws, is Boyle's law. So let's give you a taste of the type of pretty basic calculations we're going to be doing as it comes to gases. Okay, so we're going to look at Boyle's law. Is a inverse relationship between the pressure and volume of a gas. Okay. So inverse law means it changes in opposite directions. When volume increases, the pressure decreases. Okay, and this is the important part. As long as the temperature and the amount of the gas stay the same. Okay, so we're going to hold the temperature and the amount of gas the same, and that's going to allow this inverse relationship between pressure and volume. Okay. So that's what it looks like. We have a piston that you can change the volume with. So as you decrease the volume from 4 liters down to 2 liters, your pressure will double, okay, from 1 atmosphere to 2 atmospheres. Okay, and right here is a statement of Boyle's law. Pressure of system 1, volume of pressure 1 is equal to pressure of volume 2, volume of system 2. Okay, Boyle's law. Pressure 1, volume 1 is equal to pressure 2, volume 2. That's Boyle's law. Okay, and we're holding what the same? We're holding temperature and the number of particles, gas particles, constant. Okay, yeah, you know what, that looks kind of, I'm going to colon. All right. So what does that mean for our purposes? It means exactly this. We get to do calculations with it. Okay, this is just a restatement in kind of mathematical form, what we saw here in visual form as the atmospheric pressure increases, the volume decreases. That's all I was saying. Okay, and there's Boyle's law. pressure 1, volume 1 is equal to pressure 2, volume 2. You're using this right now to drive air in and out of your lungs. As your diaphragm contracts and flatten out, it's going to increase the volume. That will create a pressure differential between the outside of your body and the inside of your lungs. Air will flow down the pressure gradient into your lungs. Okay. And exact happens when the diaphragm relaxes, volume decreases, pressure increases, and exact opposite air then comes out of your mouth and nose. Okay, let's do our first calculation. Okay, so Freon, which is a refrigerant used in most refrigeration systems, certainly in your car. And they have some other gas they use now, but Freon was the big one for years and years and years. And what is the new volume of an 8-liter sample of Freon gas, initially at 550 millimeters of mercury, after its pressure is changed to 20, and we're keeping the temperature constant and the number of moles of gas constant? Okay. Okay, so let's look at this. So I have an 8-liter. Okay, 8 liters. 8 liters, 550 millimeters of mercury. Okay. And it changes to 220 millimeters of mercury, or 2,200 millimeters of mercury. I think that's what it said. Yes. Okay. Constant temperature. So, using Boyle's law, we can determine what's going on. So, let's insert our variables. We have volume 1, we have pressure 1, and we have volume 2, right? Okay, so pressure 1, volume 1 is equal to pressure 2, volume 2. Okay, what we don't have is pressure 2. Okay, so it's asking us to solve for the pressure the volume. Oh, don't scratch that. What I don't have, there we go. That's pressure to what I don't have. Sorry about that. Okay, so we have the first volume, the first pressure, the second pressure. We don't have the second volume. So let's rearrange Boyle's law so we can solve for volume. Okay, so let's divide both sides by the secondary pressure. We have pressure 1, volume 1 over pressure 2 is equal to our second volume. Okay, basic algebra. Okay, divide both sides through by pressure. Does anyone follow what I did there? Okay, excellent. So let me just rewrite that. I like my unknowns on my left. It's just a quirk of mine. Times what, volume 1? Okay. So now that we all have that clean up, we can just put in our knowns. Our pressure 1, we started at 550 millimeters of mercury. Okay, we went up to 2,200 millimeters of mercury, and our initial volume was 8 liters. Okay. Let's cross those out, cross out those out, and then that will give you your answer in liters. Yeah, actually, let's keep this going. So V2 in the number of liters. Okay. Okay, P1, PV2, we ran it solving for V2, and our answer is going to be 2 liters. Okay, which makes perfect sense, right? Since the pressure went up, the volume is going to go down. Okay, and so I will have you guys, that's probably good for today, actually. So I'll have you complete your homework assignment with the rest of class, and